Imagine standing in what is now Montana 66 million years ago. The air is thick and warm, heavy with moisture from inland seas that stretch across half the continent. The sun filters through a canopy of flowering trees, a relatively new invention in Earth's history, their bright blooms attracting insects that hum and buzz through the undergrowth. Beneath your feet, ferns carpet the forest floor in dense green waves. In the distance, you hear sounds that no human ear has ever actually heard. The low rumble of a triceratops herd moving through a clearing, their massive three-horned heads swaying as they browse on cycads and palms. The sharp cry of a pterosaur wheeling overhead, its leathery wings spanning 10 meters or more. And somewhere deeper in the forest, the heavy footfalls of something much larger. A Tyrannosaurus perhaps, the apex predator of this world, moving with surprising stealth for a creature that weighs as much as an elephant. This is the late Cretaceous, and life on Earth is thriving in forms both familiar and utterly alien. Dinosaurs have ruled the planet for over 160 million years. They've diversified into every ecological niche imaginable. Massive sauropods still lumber through forests in some parts of the world, their necks reaching heights that would make a giraffe envious. Armored ankylosaurs waddle through the underbrush like living tanks. Duck-billed hadrosaurs gather in herds that number in the thousands. Raptors hunt in coordinated packs with intelligence that rivals modern wolves. In the oceans, massive marine reptiles patrol waters teeming with ammonites, ancient cephalopods whose coiled shells come in sizes from thumbnail to tractor tire. Mosasaurs, essentially giant seagoing lizards, are the apex predators here, some growing to lengths of 15 meters. Above, the skies belong to pterosaurs, some no bigger than sparrows, others with wingspans that rival small aircraft. The world is full, productive, successful. Evolution has had millions of years to refine these forms, to test them against changing climates and shifting continents. These are not struggling species clinging to existence. These are dominant life forms at the peak of their success, and then, in geological terms, they vanish, not over millions of years, not even over hundreds of thousands of years. The evidence suggests that the majority of dinosaur species disappeared within a window that might have been as short as a few decades to perhaps a few thousand years. In a fossil record that spans hundreds of millions of years, that's functionally instantaneous. It's as if someone reached down and erased them from the planet. When the dust settled, literally and figuratively, roughly 75% of all species on Earth were gone. Every non-avian dinosaur, every pterosaur. Every mosasaur and plesiosaur, most marine reptiles, the ammonites that had survived multiple mass extinctions before, gone, many bird lineages, most mammal groups, countless plant species. The world that emerged from this event was fundamentally different from the one that went into it, quieter, emptier, waiting to be refilled. For over a century, scientists have been trying to understand what happened. The theories have ranged from the plausible to the absurd: gradual climate change, volcanic eruptions, disease, competition from mammals, even suggestions that dinosaurs simply evolved themselves into extinction, becoming too specialized to adapt. For decades, the mystery seemed unsolvable. The evidence was fragmentary, scattered across continents, buried under millions of years of sediment. Different researchers looked at different pieces and came to different conclusions. There was no consensus, no clear picture. Just a fossil record that showed thriving ecosystems on one side of a boundary and devastation on the other. Then in 1980, a father and son team made a discovery that would revolutionize our understanding not just of dinosaur extinction, but of how catastrophically and suddenly life on Earth can change. They found a thin layer of clay in a gorge in Italy. In that clay, they measured levels of a rare element that shouldn't have been there. And that measurement pointed to something that seemed almost too dramatic to be true, something falling from the sky. Tonight, we're going to explore what might be the greatest extinction mystery in the history of life on Earth. We'll look at the evidence buried in rock layers around the world, written in the chemistry of ancient sediments, and preserved in the shocked minerals that tell stories of unimaginable violence. We'll examine the theories from the widely accepted to the controversial. And we'll try to understand how a world that had belonged to dinosaurs for longer than mammals have existed since became, almost overnight, something entirely new. So settle in, because we're going back to the day the Mesozoic era ended. Before we understand what went wrong, we need to understand just how right things were going. Because 67 million years ago, the late Cretaceous world was not a planet in decline. It was a planet at what might have been one of its most productive, diverse, and successful periods in the entire history of complex life. The dinosaurs weren't struggling. They were thriving. Start with the numbers. Fossil evidence suggests that dinosaur diversity in the last few million years of the Cretaceous was at or near its highest point ever. New species were still evolving. New body plans were still being tested. In North America, the Hell Creek Formation preserves a snapshot of this world. Triceratops, with its massive frill and 3 horns, was one of the most common large animals, filling the ecological role of modern bison or wildebeest. Edmontosaurus, a duck-billed hadrosaur, gathered in vast herds that migrated seasonally. Ankylosaurus, covered in bony armor with a club-like tail, browsed on low vegetation. and stalking them all, Tyrannosaurus rex, possibly the most powerful land predator that has ever existed. These weren't evolutionary dead ends. They weren't ancient relics hanging on past their time. The fossils show healthy populations with age diversity, from juveniles to adults. They show evidence of complex behaviors, nesting sites, possible parental care, social structures. In Asia, a different but equally diverse dinosaur fauna flourished. Velociraptors and their larger relatives hunted in what is now the Gobi Desert, though at the time it was a more temperate environment with seasonal rivers and scattered forests. Protoceratops, a smaller relative of Triceratops, was so common that its fossils are sometimes found in bone beds containing dozens of individuals. Giant sauropods, the long-necked titans that had dominated the Jurassic, were less common in the northern continents by this time, but in South America and parts of Asia they were still going strong. Titanosaurs, some of the largest land animals ever to exist, were still evolving new forms right up until the end. South America had its own unique dinosaur ecosystems. Abelisaurids, predatory dinosaurs with short, deep skulls and tiny arms, filled the role that tyrannosaurs played in the north. Saltosaurus and other titanosaurs browsed on vegetation that was becoming increasingly dominated by flowering plants. The world was fragmenting into distinct biogeographic regions, each with its own evolutionary experiments, and it wasn't just dinosaurs. The oceans were full of life. Mosasaurs had evolved from land-dwelling lizards only about 30 million years earlier, and by the end of the Cretaceous, they had diversified into dozens of species ranging from small fish-eaters to massive apex predators. Some had specialized teeth for crushing shellfish. Others had streamlined bodies for pursuing fast-swimming prey. Plesiosaurs, with their long necks and paddle-like limbs, still patrolled the seas, though they were less diverse than they had been earlier in the Mesozoic. Sea turtles, some with shells over 4 meters long, swam through warm tropical waters. The ammonites, those cold-shell cephalopods related to modern nautilus, had survived multiple extinction events over hundreds of millions of years. In the late Cretaceous, they came in an astonishing variety of forms. Some had shells that were loosely coiled or even straight. Others had elaborate ribs and spines decorating their shells. They ranged from the size of a coin to the size of a car tire. They were everywhere in every ocean at every depth. Above the water, pterosaurs had reached their maximum size. Quetzalcoatlus, with a wingspan of perhaps 10 to 11 meters, was the largest flying animal that has ever existed. These weren't clumsy gliders. Recent research suggests they were sophisticated flyers capable of powered flight, launching themselves from the ground with their powerful forelimbs and soaring on thermals for hundreds of kilometers. Smaller pterosaurs filled niches that today belong to seabirds and shorebirds, and birds themselves were diversifying. By the end of the Cretaceous, several modern bird lineages had already appeared. Ancestors of ducks, shorebirds, and other groups were present alongside more archaic toothed birds and the last of the enantiornithines, a group of birds that would not survive the extinction. On land, flowering plants had been around for perhaps 40 million years by this point, and they were in the process of transforming terrestrial ecosystems. Forests of oak, maple, and magnolia were spreading across the continents. Grasses hadn't evolved yet, but there were dense ground covers of ferns and low shrubs. The partnership between flowering plants and insects was driving an explosion of diversity in both groups. Bees, butterflies, and countless other pollinators were evolving alongside the plants they serviced. Mammals were there too, small and mostly nocturnal, but more diverse than often assumed. Some were insectivores, others herbivores, a few possibly omnivores. They ranged in size from mouse-like creatures to animals as large as modern badgers. They weren't dominant, but they were successful in their own niches, waiting in the ecological shadows. The climate was warm, warmer than today by several degrees globally. There were no permanent ice caps at the poles. Sea levels were high, flooding large parts of the continents and creating shallow inland seas. The western interior seaway split North America down the middle from the Arctic to the Gulf of Mexico. These warm, shallow seas were incredibly productive, supporting rich ecosystems of fish, marine reptiles, and invertebrates. Carbon dioxide levels were higher than today, though not catastrophically so. The greenhouse effect kept temperatures relatively stable and warm even at high latitudes. Forests grew in what is now Alaska and Antarctica. Dinosaurs lived within the Arctic Circle, though they may have migrated seasonally to avoid the long polar nights. This was a world in balance. Predators and prey, plants and herbivores, ocean and land ecosystems, all interconnected in complex webs that had been refined over millions of years. There were no obvious signs of system-wide stress, no clear evidence that the dinosaurs were in decline or that the ecosystems were failing. Volcanic activity was high in some regions, particularly in what is now India, where the Deccan traps were beginning to erupt, but volcanic episodes had happened before without causing mass extinctions. The climate was shifting slightly, becoming marginally cooler in some regions, but nothing dramatic, nothing that would predict what was about to happen. And then, on what may have been an otherwise ordinary day in late spring or early summer, something appeared in the sky, moving faster than anything that had ever moved through Earth's atmosphere before, burning as it fell, heading toward what is now the Yucatan Peninsula in Mexico. The seconds before impact, any creature unlucky enough to be looking up would have seen a fireball brighter than the sun, growing larger with terrifying speed. There would have been no time to run, no time to hide, no time to do anything but exist for one final moment in a world that was about to end. The object, an asteroid or possibly a comet, was roughly 10 to 15 kilometers across. Not particularly large by cosmic standards, but more than large enough for what was about to happen. It was traveling at perhaps 20 kilometers per second, maybe faster. At that speed, the atmosphere might as well not exist. The object barely slowed as it punched through the air, creating a tunnel of superheated plasma behind it. When it struck the shallow sea off the coast of what is now Mexico, it hit with the force of roughly 100 million megatons of TNT. To put that in perspective, the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, released about 50 megatons. This impact was 2 million times more powerful. In the first second, the asteroid vaporized, not shattered, not fragmented, vaporized, turned into a ball of superheated gas and plasma. The rock beneath the impact site vaporized too. Limestone, granite, whatever was there simply ceased to exist as solid matter. The energy release created a crater that would eventually measure about 180 kilometers across and 20 kilometers deep, though it wouldn't stay that shape for long. The impact excavated a hole in the Earth's crust. The shockwave from the impact traveled outward through the rock itself faster than the speed of sound. In the first few minutes, everything within perhaps 1,500 kilometers of the impact site was obliterated. Not killed, obliterated. The rock itself was liquefied or vaporized. Any living thing within that radius simply ceased to exist, transformed into plasma or scattered as atoms. But the destruction was just beginning. The impact threw an unimaginable amount of material into the atmosphere. Rock, water, vaporized asteroid, all of it flung upward at velocities that exceeded escape velocity. Some of the ejecta literally left Earth's atmosphere, traveling into space before falling back down. As this material re-entered the atmosphere all around the planet, it heated the air to oven-like temperatures. Within hours, perhaps less, the sky everywhere on Earth would have been filled with streaks of light, like a meteor shower but millions of times more intense. The radiant heat from all this re-entering material may have been enough to ignite wildfires across entire continents. Forests that had stood for millions of years burst into flame. Animals with nowhere to hide were cooked alive. The thermal pulse lasted for hours, a global broiler that turned the sky itself into a weapon. Seismic waves from the impact, far more powerful than any earthquake in human history, radiated outward through the Earth's crust. When they reached the other side of the planet, they converged and focused, creating intense ground shaking that may have triggered volcanic eruptions and landslides. Tsunamis generated by the impact were hundreds of meters tall in the Gulf of Mexico. As they spread outward, they were still tens of meters high when they struck coastlines thousands of kilometers away. The western interior seaway, that shallow sea splitting North America, would have sloshed back and forth like water in a bathtub, with waves surging inland and then retreating, carrying everything with them. Coastal ecosystems around the world were scoured clean. In the hours after the impact, the sky darkened. The material thrown into the upper atmosphere, tiny particles of rock and soot, began to spread around the globe. Within days, perhaps less, sunlight was significantly dimmed. Within weeks, it may have been reduced to twilight levels even at midday. Photosynthesis slowed, then stopped. Plants began to die. Without plants, herbivores began to starve. Without herbivores, carnivores followed. The impact winter had begun. Temperatures plummeted. Not to ice age levels necessarily, but enough to stress organisms that had evolved in a greenhouse world. The combination of cold and darkness was lethal. In the oceans, the situation was even worse. The impact had vaporized sulfur-rich rocks, throwing vast amounts of sulfur dioxide into the atmosphere. This combined with water vapor to form sulfuric acid, which fell as acid rain. Ocean surface waters became acidic enough to dissolve the shells of many marine organisms. Plankton, the base of the ocean food web, died in massive numbers. The ammonites, with their calcium carbonate shells, were particularly vulnerable. Marine reptiles, already stressed by the collapse of their prey base, had nowhere to go and no way to adapt quickly enough. On land, the picture was similarly grim. The fossil record shows a sharp boundary, a thin layer of sediment that marks the transition from the Cretaceous to the Paleogene. Below this layer, dinosaur fossils are common. Above it, they disappear. In some locations, this boundary layer is just a few centimeters thick. In it, scientists have found shocked quartz, tiny mineral grains that show microscopic fracture patterns that only form under the extreme pressures of an impact or nuclear explosion. They've found tektites, small glassy spheres created when molten rock is flung through the air and cools rapidly. They've found a thin layer of clay enriched in iridium, that rare element that is much more common in asteroids than in Earth's crust. And they've found soot, vast amounts of it, evidence of the global wildfires that swept across continents in the aftermath. This is the story that emerged from decades of research, from thousands of scientific papers, from evidence gathered at hundreds of sites around the world. It's a story of catastrophic, sudden global devastation. A story of a world that changed in a day and died over the following months and years. But it's not the only story. Because even as the impact hypothesis gained acceptance, questions remained. The timing wasn't perfect. Some dinosaur groups seemed to be in decline before the impact. The Deccan Traps volcanism in India was pumping massive amounts of gas into the atmosphere for hundreds of thousands of years before and after the impact. And some groups of organisms that should have died didn't, while others that should have survived vanished. The extinction event is real. The impact is real. But whether the impact alone explains everything, or whether it was the final blow in a longer, more complex story, that's where the debate continues. And that's where we need to look more carefully at what the rocks actually tell us. The first clue that something extraordinary had happened at the end of the Cretaceous came not from paleontologists, but from a geologist and his physicist father. In the late 1970s, Walter Alvarez was studying rock layers in a gorge near the town of Gubbio in Italy. He was interested in the rates at which sediments accumulated on ancient seafloors, and he noticed something odd. Between the Cretaceous and Paleogene layers, there was a thin band of clay, maybe a centimeter thick. It was darker than the limestone above and below it, and it seemed to represent a period where almost nothing was accumulating except fine clay particles. Walter mentioned this to his father, Luis Alvarez, a Nobel Prize-winning physicist. Luis suggested they could measure how long it took for that clay layer to form by measuring the amount of iridium in it. Iridium is an element that's rare in Earth's crust but relatively common in meteorites. It rains down on Earth constantly as cosmic dust, accumulating in sediments at a slow, steady rate. If you know the background accumulation rate, you can use iridium as a kind of clock. The more iridium in a layer, the longer it took to form. When they ran the analysis, the results made no sense. The clay layer didn't just have more iridium than the layers above and below. It had vastly more, perhaps 30 times the background level. That much iridium couldn't have accumulated slowly. It had to have been deposited all at once. And the only plausible source for that much iridium delivered suddenly was an extraterrestrial impact. In 1980, the Alvarez team published their findings and proposed that an asteroid roughly 10 kilometers across had struck Earth at the end of the Cretaceous, causing the mass extinction. The reaction from the scientific community was skeptical, often hostile. The idea that catastrophes from space could shape Earth's history ran counter to the prevailing view that geological processes were slow and gradual. Many paleontologists argued that the dinosaur extinction had been gradual, not sudden, and that an impact couldn't explain the selectivity of what survived and what didn't. But the Alvarez team had evidence, and it was reproducible. Other researchers began looking for the iridium anomaly in their own rock samples. They found it in Montana, in New Mexico, in Denmark, Spain, New Zealand. Everywhere researchers looked at the boundary between the Cretaceous and Paleogene, there was an iridium spike. The pattern was global. Whatever had deposited that iridium had affected the entire planet. Then came the shocked quartz. Geologists examining boundary layer sediments under microscopes found quartz grains with distinctive microscopic fracture patterns, sets of parallel lines crisscrossing the crystal structure. These shock lamellae only form when quartz is subjected to pressures far beyond anything normal geological processes can produce. They're found at nuclear test sites and at known impact craters. Their presence in the boundary layer was strong evidence for a massive impact. Tektites and microtektites, tiny glassy spheres formed from rock melted and flung through the air, were found in boundary layers around the Caribbean and Gulf of Mexico. Their chemical composition and distribution suggested they had originated from an impact somewhere in that region. The evidence was mounting, but there was a problem. Where was the crater? An impact large enough to cause a global extinction should have left a scar on the Earth's surface, a massive crater that would be visible even millions of years later. Researchers began searching. They looked at known impact structures, but none were the right age. They looked at satellite imagery and geophysical data, searching for circular features or gravitational anomalies that might indicate a buried crater. For nearly a decade, the crater remained elusive. Some scientists suggested it might have struck in the ocean and been subducted beneath a tectonic plate, erasing the evidence. Others wondered if the impact had been smaller than thought, or if there had been multiple impacts. Then in 1991, the crater was found, or rather, it was recognized. Geophysicists working for the Mexican State Oil Company had identified a large circular structure buried under the Yucatan Peninsula decades earlier. They had called it Chicxulub after a nearby town and assumed it was volcanic, but when researchers re-examined the data in light of the impact hypothesis, everything clicked into place. The structure was the right size, roughly 180 kilometers across. it was in the right location to explain the distribution of tektites and shocked quartz. Core samples from the structure showed the characteristic features of impact craters: shocked minerals, melted rock, breccias containing fragments of both terrestrial and extraterrestrial material. And crucially, it was the right age. Dating of the impact melt rocks gave an age of 66.043 million years, with an uncertainty of only about 11,000 years. That matched, within the limits of measurement, the age of the boundary layer around the world. Chicxulub was the smoking gun, the crater that proved the Alvarez hypothesis. An asteroid had indeed struck Earth at the end of the Cretaceous, and it had struck with enough force to leave a scar that would remain visible, buried under sediment for 66 million years. But finding the crater didn't end the debate, it just shifted the questions. Yes, there was an impact, yes, it was catastrophic, but did it really cause the extinction, or was it just one factor among many? Because the more researchers looked at the timing and pattern of extinctions, the more complicated the picture became. Some dinosaur groups seemed to be declining in diversity for millions of years before the impact. In North America, the number of dinosaur species appears to drop in the last few million years of the Cretaceous, though whether this is a real decline or an artifact of an incomplete fossil record is debated. Plant fossils show changes in the last million years before the boundary, with some groups declining and others expanding. Marine ecosystems were under stress. Sea levels were falling as the climate cooled slightly. The shallow inland seas that had covered large parts of the continents were retreating, reducing habitat for marine organisms. Some groups of ammonites were already declining before the impact, and then there's the Deccan Traps. This is one of the largest volcanic provinces on Earth, a region in what is now India where massive eruptions poured out more than 1 million cubic kilometers of lava over a period of perhaps 1 million years. The main phase of eruptions happened right around the time of the extinction, perhaps starting a few 100,000 years before the impact and continuing for several 100,000 years after. Volcanic eruptions on this scale don't just produce lava. They pump enormous amounts of gas into the atmosphere: sulfur dioxide, which forms sulfate aerosols that cool the climate, carbon dioxide, which warms it over longer timescales, volcanic ash that can dim sunlight and disrupt photosynthesis. For decades, some researchers have argued that the Deccan Traps volcanism, not the Chicxulub impact, was the primary driver of the extinction. Or at least that volcanism had already weakened ecosystems, making them more vulnerable when the impact struck. The debate became contentious. Impact proponents pointed to the sudden nature of the extinction in the fossil record and the clear global signature of the impact. Volcanism proponents pointed to the longer-term changes in climate and ecosystems and argued that impacts alone don't explain the selectivity of the extinction. Why did some groups die while others survived? Why did birds make it through but non-avian dinosaurs didn't? Why did crocodiles and turtles, which should have been vulnerable to the environmental disruption, survive relatively unscathed? These are not easy questions. The extinction was selective in ways that are hard to explain with any single mechanism. Large animals died at higher rates than small ones, which makes sense if food chains collapsed. Marine organisms with calcium carbonate shells were hit harder than those without, consistent with ocean acidification from the impact. But freshwater organisms, fish, turtles, crocodiles, survived at much higher rates than their marine cousins. Why? One possibility is that freshwater ecosystems are buffered against rapid environmental change. Rivers and lakes receive nutrients from the surrounding land, so even if photosynthesis stopped globally, there would still be organic matter washing into freshwater systems. Detritus-based food chains, which don't depend directly on living plants, could sustain communities of scavengers and predators. Another mystery is the survival of some bird lineages. Birds are dinosaurs, the only dinosaur lineage that made it through the extinction, but not all birds survived. The toothed birds and enantiornithines went extinct. Only the lineages that would eventually give rise to modern birds made it through. Was it something about their ecology, their size, their ability to survive on seeds which can remain viable for years even in harsh conditions? The pattern suggests that whatever happened, it wasn't a simple on-off switch, it was a filter. And understanding what that filter selected for and against is key to understanding the extinction itself. Recent research has tried to integrate the impact and volcanism hypotheses into a more comprehensive picture. Perhaps the Deccan Traps eruptions had been stressing ecosystems for hundreds of thousands of years, causing gradual declines in some groups and pushing the climate into a more variable, unstable state. Then the Chicxulub impact delivered a sudden, catastrophic blow to a system that was already weakened. The combination, not either factor alone, caused the mass extinction. This makes sense from a system's perspective. Complex ecosystems have resilience. They can absorb shocks and disturbances up to a point, but if they're already stressed, if their resilience has been eroded by long-term pressures, then a sudden additional shock can push them past a tipping point. The volcanism hypothesis also helps explain some of the longer-term patterns in the fossil record. The recovery after the extinction took millions of years. Ecosystems didn't just bounce back. They had to rebuild from the ground up, and during that recovery, there's evidence of continued environmental instability, which could be explained by ongoing Deccan Traps eruptions releasing gases into the atmosphere for hundreds of thousands of years after the impact. So the story that emerges is not simple. It's not a single asteroid killing the dinosaurs. It's a world already under stress from volcanism and climate change, dealt a sudden, devastating blow by an impact that pushed it over the edge into mass extinction. The impact was the trigger, but the gun had been loaded by longer-term processes. This more nuanced view is gaining acceptance, though debates continue over the details. How much did volcanism contribute? How much was the impact? Were ecosystems really in decline before the impact, or were they just experiencing normal fluctuations? Different researchers looking at different data sets still come to different conclusions, and that's where the story stands today. We know an asteroid struck Earth 66 million years ago. We know it caused catastrophic environmental disruption. We know that roughly 75% of species went extinct in a geologically brief interval. What we're still working out is the exact sequence of events, the relative importance of different factors, and why some organisms survived while others didn't. The rocks hold the answers, but reading them requires patience, careful analysis, and a willingness to revise our understanding as new evidence comes to light, and new evidence continues to emerge. Researchers drilling into the Chicxulub crater itself have recovered cores from the peak ring, the circular ridge of uplifted rock inside the crater. Analysis of these cores is revealing details about the impact itself, the composition of the target rocks, the temperature and pressure conditions immediately after impact. Other teams are studying the boundary layer at sites around the world, looking for chemical signatures that can tell us about the state of the atmosphere and oceans in the years and decades after the impact. Still others are refining the dating of both the impact and the Deccan Traps eruptions, trying to nail down the exact timing of events. Every new piece of data adds to the picture, sometimes confirming existing hypotheses, sometimes complicating them. Extinction event is no longer a simple mystery with a simple answer. It's a complex event with multiple causes, playing out over different timescales, affecting different organisms in different ways. But if the cause is complex, the consequences are clear. The world that emerged from the extinction was fundamentally different from the one that went into it. And understanding that transformation means looking at what survived and what didn't, and how life rebuilt itself in the aftermath. When the dust settled, literally and figuratively, the world was quiet in a way it hadn't been for over 160 million years. The thundering footsteps of sauropods, the roars of tyrannosaurs, the calls of pterosaurs wheeling overhead, all of it was gone. The Mesozoic era, the age of dinosaurs, had ended. The Cenozoic era, the age of mammals, was about to begin, but it didn't begin immediately. The first few million years after the extinction were a time of ecological devastation and slow, painful recovery. In the fossil record, this shows up as a period where diversity is low and ecosystems are simple. The boundary layer itself, that thin band of clay enriched with iridium and shocked quartz, is often nearly barren of fossils. Immediately above it, the first fossils to appear are often ferns. Fern spores dominate the pollen record in many locations, a phenomenon called the fern spike. Ferns are pioneer species, among the first plants to colonize disturbed ground. After volcanic eruptions or landslides, ferns moving quickly, their spores carried by wind, their rhizomes spreading through the soil. The global fern spike suggests that the extinction had created a world of disturbed ground, of landscapes stripped of their vegetation, waiting to be recolonized. Slowly, other plants returned. Flowering plants, which had been diversifying rapidly in the Cretaceous, recovered relatively quickly. Their seeds could survive buried in soil or transported by wind and water. Within perhaps a few tens of thousands of years, forests were beginning to regrow, but they were different forests. Some plant families that had been common in the Cretaceous were gone or greatly reduced. Others that had been minor players expanded to fill the empty niches. In the oceans, the recovery took longer. The extinction had wiped out the ammonites entirely, along with most marine reptiles. The oceans were left to fish, sharks, and a few groups of marine mammals that would eventually evolve from land-dwelling ancestors. Plankton diversity was devastated, and it took millions of years for the base of the marine food web to recover fully. Coral reefs, which had been hit hard by the ocean acidification, took even longer. On land, the small mammals that had survived began to diversify. In the Paleocene, the epoch immediately following the extinction, mammal diversity exploded. Within a few million years, mammals had evolved into forms ranging from tiny insectivores to large herbivores the size of pigs or sheep. They were filling the niches left vacant by the dinosaurs, but they were doing it in their own way, with their own body plans and adaptations. Birds also diversified rapidly. The lineages that survived the extinction gave rise to most of the bird groups we see today. Waterbirds, raptors, songbirds, all of them trace their ancestry back to the few bird lineages that made it through the extinction. In a sense, the dinosaurs didn't go entirely extinct. They just became smaller, feathered, and capable of flight. Crocodiles and turtles, which had survived the extinction with relatively little loss, continued on much as they had before. Their body plans, refined over millions of years, proved resilient to the environmental catastrophe. Lizards and snakes, also relatively unaffected, diversified in the new ecosystems. But the world they inherited was not the warm greenhouse of the late Cretaceous. The climate was cooler, more variable. The inland seas had retreated, leaving large continental interiors that experienced more extreme seasonal temperature swings. The ecosystems were simpler, less productive, at least initially. It would take millions of years for the Earth to rebuild the ecological complexity that had been lost. From a human perspective, looking back across 66 million years, it's hard not to see the extinction as a kind of reset button. The dominant life forms were erased and new ones took their place. The dinosaurs' reign ended and the age of mammals began. But from the perspective of the organisms living through it, it was simply survival or death. There was no grand plan, no purpose. Just a catastrophic environmental disruption and the question of whether any given organism could endure it. The selectivity of the extinction offers clues about what traits favored survival. Small size seems to have helped. Small animals need less food, can shelter in burrows or underwater, and can survive on a wider variety of resources. The ability to eat seeds, detritus, or dead organic matter was an advantage when fresh plant growth stopped. Aquatic organisms, especially those in freshwater environments, had higher survival rates than terrestrial ones. The ability to enter dormancy, to shut down metabolism and wait for better conditions, would have been valuable. Looking at the survivors, a pattern emerges. Generalists survived, specialists died. Organisms that could adapt, that could switch food sources or habitats, made it through. Those that depended on specific plants, specific prey, or specific environmental conditions were more likely to go extinct. This makes sense in the context of a rapidly changing environment. When the world is stable, specialization is rewarded. You can fine-tune your adaptations to exploit a specific niche more efficiently than any competitor. But when the world changes suddenly, specialization becomes a liability. If your food source disappears, you starve. If your habitat is destroyed, you have nowhere to go. The dinosaurs, for all their success, may have been victims of their own specialization. After 160 million years of evolution, they were exquisitely adapted to the world of the late Cretaceous. But that world disappeared in a matter of months or years, and they couldn't adapt fast enough. The mammals, small and generalized, survived in part because they were less specialized, less dependent on specific conditions. It's a sobering thought. Success in stable times can become a death sentence when conditions change rapidly, and it raises questions about our own species. Humans are highly adaptable in some ways, capable of surviving in almost any environment on Earth. But our civilization is specialized, dependent on stable climate, reliable agriculture, complex supply chains. What would happen if those conditions changed suddenly? The extinction of the dinosaurs is not just a story about the past. It's a reminder that life on Earth has always been subject to catastrophic disruptions, and that survival often depends not on being the strongest or most successful, but on being adaptable when everything changes at once. And change, as the geological record shows, is the only constant. The Earth has experienced 5 major mass extinctions in the past 500 million years and numerous smaller ones. The Cretaceous extinction, as devastating as it was, wasn't even the worst. That distinction belongs to the Permian extinction 252 million years ago, which killed roughly 90% of all species. Each time life has recovered, new forms have evolved to fill empty niches. Ecosystems have rebuilt themselves, but the recovery takes time, millions of years, and the world that emerges is never quite the same as the one that was lost. The dinosaurs are gone except for their bird descendants, but their legacy remains. In the rocks, in the fossils, in the crater buried under the Yucatan, and in the questions they leave us with about how life responds to catastrophe, about what it takes to survive when the world ends, and about what comes next. For us, the story of the dinosaur extinction is both distant and immediate. Distant because it happened 66 million years ago, in a world so different from ours that it's hard to imagine. Immediate because the mechanisms that caused it, asteroid impacts, volcanic eruptions, rapid climate change, are still active. The Earth is still a dynamic, sometimes violent planet. Asteroids still cross our orbit, volcanoes still erupt. The climate is changing, though now for different reasons. The question is not whether catastrophic events can happen. The geological record proves they can and do. The question is whether we, with our technology and our understanding of the past, can see them coming and prepare. We now track near-Earth asteroids, cataloging those that might pose a threat. We monitor volcanic activity and try to predict eruptions. We study past climate changes to understand how the Earth's systems respond to different forcings. In a sense, we're using the dinosaur extinction as a lesson, a case study in planetary catastrophe. We're trying to learn from their fate so we don't share it, but there's a deeper lesson too. The dinosaurs didn't cause their own extinction. They were victims of bad timing, of being in the wrong place when an asteroid happened to strike. We, on the other hand, are actively changing our planet's climate, altering its ecosystems, driving species extinct at rates that rival the great mass extinctions of the past. We have become, in a sense, our own asteroid. The end Cretaceous extinction shows us what a world in collapse looks like, ecosystems unraveling, food chains breaking, species disappearing, and it shows us how long recovery takes. The Earth recovered from the dinosaur extinction, but it took millions of years. Humans don't have millions of years. Our civilizations, our agriculture, our entire way of life depends on the relatively stable climate of the past 10,000 years. If we push the Earth's systems too far, if we trigger cascading changes that we can't control, we may find ourselves living through our own version of the extinction event, not caused by an asteroid from space, but by our own actions. That's the uncomfortable parallel. The dinosaurs couldn't have prevented their extinction. We can prevent ours, or at least mitigate it, but only if we pay attention to the lessons written in the rocks, only if we understand that the Earth's systems, for all their resilience, have limits. Push them past those limits and the consequences can be catastrophic, sudden, and irreversible on human timescales. So as you lie there in the dark, drifting towards sleep, consider the world 66 million years ago. A world full of life, of vast herds and massive predators, of forests and oceans teeming with organisms that had never known anything but success. And then in a single day, a rock from space ended it all. The impact, the fires, the darkness, the cold, the slow starvation as ecosystems collapsed, the extinction of giants that had ruled the Earth for longer than mammals have existed since. It's a story of how quickly everything can change, of how fragile even the most successful life forms can be when the environment shifts beneath them. And it's a reminder that we live on a planet that is still capable of sudden, violent change. The dinosaurs are gone. Their world is gone, but the Earth remains spinning through space, orbiting the sun, still subject to the same physical laws, the same cosmic hazards. We have the advantage of knowledge, of understanding what happened and why. We can look at the iridium layer, the shocked quartz, the crater, and know that an asteroid strike caused a mass extinction. We can study the Deccan traps and understand how volcanism can alter climate. We can read the fossil record and see which organisms survived and which didn't and learn from their fate. That knowledge is both a gift and a responsibility. A gift because it allows us to prepare, to watch the skies, to understand our planet. A responsibility because it means we can no longer plead ignorance. We know what can happen. We know the Earth's history is punctuated by catastrophes. And we know that the choices we make now will determine whether our species and the ecosystems we depend on survive the next million years. The dinosaur extinction is not just ancient history. It's a mirror reflecting our own vulnerabilities, our own dependence on a stable environment. And it's a warning written in stone that nothing lasts forever, that dominance is temporary, and that survival often depends on being in the right place at the right time, or having the adaptability to endure when everything changes. So rest easy knowing that tonight at least no asteroid is headed our way. The skies are clear. The planet is stable, relatively speaking. Tomorrow will come and the sun will rise just as it has for billions of years. But somewhere in the back of your mind, keep that image of the late Cretaceous world, thriving and successful right up until the moment it wasn't. And remember that the story of life on Earth is not one of steady progress, but of sudden disruptions and slow recoveries, of extinctions and rebirths, of endings and beginnings. The dinosaurs had their time. They had 160 million years, which is longer than any mammal lineage has managed so far, and when their time ended, life went on. Different life, new life, but life nonetheless. The planet survived, evolution continued. And eventually, millions of years later, a species of clever apes evolved that could look back at the dinosaur extinction, study it, understand it, and learn from it. That species is us. And the question now is what we'll do with that knowledge, whether we'll heed the warnings written in the rocks, or whether we'll become another thin layer in the geological record, a brief spike in the fossil record followed by absence. The choice, unlike for the dinosaurs, is ours to make. And as you drift off to sleep, that thought can be either comforting or unsettling, depending on how you look at it. Comforting because it means we have agency, the ability to shape our own fate. Unsettling because it means we bear the responsibility for what comes next. Either way, the dinosaurs are waiting in the rocks, frozen in stone, their story told in fossils and iridium and shocked quartz. A story of dominance and disaster, of success and sudden end. A story that echoes across 66 million years to remind us that we too are part of the same story, the same long, unfinished tale of life on a restless planet. Sleep well. The dinosaurs can't hurt you now. They've been gone for 66 million years, but their lesson remains carved into the earth itself, waiting for anyone willing to listen. The world can change in a day, and when it does, only the adaptable survive.